Welcome to chapter 2, which is about acids and bases. At the beginning of this chapter, I will briefly talk about what you learned already in general chemistry, and it's about the acid-base theories. You know 3 of them by now. We just work on 2, Brunson and Lowry, and Lewis theory. The first one is Brunson and Lowry. The key to know about the acidity and basic properties is to know the theories really well and the definition of acids and bases based on these 2 theories. So according to Brunson-Lowry theory, acid is a compound which is a proton donor. What do we call a proton? We don't talk about the particle. We are talking about the hydrogen ion, which we call it proton. And then base is a proton acceptor. That's what you knew. So we have 2 types of acids and 2 types of bases, strong acids and weak acids. How do we distinguish between strong acids and weak acids? Is that let me just make a quick change here to go over it together. All right, so the difference between strong acids and weak acids is this arrow that you see here. The 100% association one-way arrow shows complete ionization of acid. So if this HCl is a proton donor, it's going to lose its proton and it will give it to water. So water will end up having 3 hydrogens, and because it has absorbed a positive proton, there would be a positive charge on oxygen. A weak acid like acetic acid is going to be partially ionized. You see, it's less than 100% ionization, and a part of reaction goes back. Means CH3COH, acetic acid, which acts as an acid, and later on you will see that this is the acidic hydrogen. Why is the acidic hydrogen? Because it's connected to an electronegative element, oxygen. So oxygen pulls the electrons, and this oxygen-hydrogen bond is very loose and lets the hydrogen to be released fast. So what happens is that we will end up having this ion, and hydrogen is going to stick to water. So we will have H3O positive, but because it's a weak acid, after this ion and the hydronium ion are formed, a part of the reaction is going to go back to form the acetic acid and water again. All right? The strong bases like NaOH, we said they are the proton acceptors, or you just here in this situation, you just can say it releases OH. Here, a weak base can accept the proton here. So you will have the proton is accepted from water. So it's going to be NH4 plus OH negative. So you see in both, the product is an OH in the solution. And again, the weak base is not completely dissociated. So a part of NH4 and OH will go back to formation of ammonia and water. So can you work on the rest of them on page 1 on the strong acids and bases? I'm sure you can. You have HNO3 plus H2O, which is a strong acid. So it just needs a one-way arrow. It's going to form nitrate ion plus H3O. KOH, I'm still working on page 1. KOH is a strong base. So it's potassium and OH. About the weak acid and weak base, if you have H2CO3 plus H2O, if it is the weak acid, So it's going to release one of the hydrogens. You will have HCO3. A positive proton hydrogen will be deducted, so the charge will be negative, and the hydrogen will be added to water, H3O. So that was the weak acid. And about the weak base, and you will learn in organic chemistry, nitrogen containing compounds, most of the times, 99.9% of the times, they are bases. So this weak base is going to accept a proton, C5H5NH positive. The lone pair of electrons are used to form a bond between nitrogen and hydrogen. So a positive charge will remain on nitrogen because it absorbed the hydrogen proton. And OH will be released. So, you remember from Chem 2 that for weak acids and bases, you can write K equilibrium, acidic constant. So, for example, for H2CO3, you will write down for this. You will write down KAEs, you remember, the molar concentration of products divided by molar concentration of the reactants. The only thing that we do not write in the K equilibrium is what? The liquids, like water, because their concentration does not change. Liquids and solids, we do not mention them. For Chem 2, you should remember, it shouldn't be a long time since you had Chem 2. Okay, we're still working on Bronsted-Lowry theory, and if you remember, the most important thing about Bronsted-Lowry theory is to determine their conjugate acid-base pairs. So let's see how it works. Working on page 2. Let's work on the first example to talk about the conjugate acid-base pair. Oops. Let's determine the acid and base on the left side. On the left side, if we compare CH3COOH with CH3COO, what happened? This compound has donated one proton, so this is our acid, right? Between H2O and H3O, what happened? It accepted the proton, so it's a base. Okay? Now, if we say we are dealing with the weak acids and bases, right? If we go back from the right to the left, CH3COO can accept the proton and change to CH3COOH, right? So on the other side, CH3COO is the base, and H3O can donate a proton, can lose a proton to go back to H2O form. So it will act as acid. Now you see there is a relationship between the acidic form on the left side and basic form on the right side. And the same for H2O and H3O, base and acid. So we call these pairs conjugate pairs, conjugate acid-base pairs, conjugate pair. And you're supposed to determine them and know how to determine them. You already had them in general chems, nothing new. So, the check for our work is that we definitely have one acid, one base, one donor, one acceptor. If we have a donor, we should have an acceptor. On one side and the same on the other side, one acid, one base. You cannot have two acids or two bases on the same side. And the relation between conjugate pairs is if HA is the acid with hydrogen. Base has the same anion but without one hydrogen. So the difference between a conjugate acid-base pair is just one hydrogen, as you see here. This is the acid, this is the base, so the difference is one hydrogen. H3O is the acid, H2O is the base, so the difference is one hydrogen ion. So for example, H2S and HS are a conjugate acid-base pair because the anion is the same, but the difference is one hydrogen. But H2S and sulfide, is the difference two hydrogens or one hydrogen? Two hydrogens. So these two cannot be a conjugate acid-base pair. Let's move on to the rest of page 2. See what's going on with the rest. Let's work on the third one because the second one is written for you. H3O plus H2O. You're supposed to fill in the blanks. These are good questions for the exam also. So let's see what happened. H3O changed to H2CO3. So it has accepted the proton. This is the base, huh? And this is the acid. Correct? So if it is acid, it has lost a hydrogen ion. So we have OH. So here is going to be its conjugate acid. And for H2O, OH is the conjugate base. You should be able to determine the acids and bases and also the relation between the conjugate pairs. Let's work on the next one, and I will leave the last one for you. Again, another nitrogen-containing compound. I told you nitrogen-containing compounds, if they don't have extra hydrogens, they will definitely be the base. So this is what has happened here. This compound has accepted the proton, so acts as a base. So water should be your acid. It has donated a proton, which makes it OH. And on the other side, we are dealing with acid here. These are the conjugate acid-base pair, and OH is the base, the conjugate pair for this one. Don't forget to determine each of these four Bernstein-Lowry theory for yourself. Now it's time to talk about acidic strength, to determine which one is a strong acid, which one is a strong base, based on what. If you consider weak acid, the formula like this, and the water is going to not completely dissociate to A and H3O. So how would you write the K equilibrium? We say K acidic is the concentration of the products divided by concentration of the reactants minus the solvents or the liquid and solid. So water, we never write water because it's our main component. Okay, so based on Ka, if we are given the Ka values and we want to determine the acidic strength, Ka, the higher Ka means the top of the fraction is higher, means the acid has produced more products, right? Producing more products means more dissociation, means the acid is stronger. So, strong acids have high Ka. One more time. High Ka means the top of fraction, mathematically means top of fraction is higher. This means the production is higher and the acid has dissociated more towards the product. So it means that it was a stronger acid to be able to dissociate better. Now, sometimes instead of Ka, you see pKa. 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 What is the relation between Ka and pKa? P of everything is minus log of that quantity. So let's determine the relation between pKa and acidic strength. So far we know that higher Ka, stronger acid, right? Let's see what happens to pKa. We're working on page 3 on acetic acid, CH3COOH. Ka is 1.8 times 10 to negative 5, and formic acid HCOOH. Ka is 1 times 10 to negative 4. So if we want to judge based on the Ka values, which one has a higher Ka? 10 to negative 4 or 10 to negative 5? Of course you would say 10 to negative 4. But let's find their pKa values. So pKa, which is minus log of Ka, minus log of 1.8 times 10 to negative 5 for acetic acid is 4.74. And pKa for formic acid, minus log of 1 times 10 to negative 4 is going to be 4. So the higher the Ka, the lower the pKa. We just said formic acid is stronger, right? But its pKa is smaller. So the lower the pKa, stronger acid. Now, you have more freedom on determining the strength of the acids or the strength of acids, because if the Ka is given, look for the higher Ka. If pKa is given, look for the lower pKa. Okay, that part was a review on what you had in general chem. I want you to go over them again, because for the rest of this study guide, we are going to talk about organic acids and bases, and we will go over the Lewis theory. So make sure you have worked on this part, because the rest of this study guide depends on this.